Great. Well, awesome. It's really great to be here. Really looking forward to the discussion afterwards as well. So I'm Katie. I'm the healthcare and life sciences lead at Hugging Face. We're an open source platform for machine learning. And today I'll be talking about really about evaluating these generative AI models and evaluating their potential roles in medicine, especially beyond the USMLE, which we've heard a lot of people talk, over the last year about passing USMLE as a benchmark. But where do we really go from here? That's what I'll be discussing in my talk today. And so to get started, I actually want to first ask this question. What comes to your mind when you read these words? Apple green birefringence, chocolate agar, fava beans, poda orange, which means going to be orange. And if you maybe don't have a medical background, you might be thinking of different types of ingredients, potentially for some strange menu. But if you're a second-year medical student, immediately you're going to be thinking about certain pathologies or pathogens. And this is because you are studying for step one and you're reading a ton of textbooks, you're doing a ton of flashcards, and you're learning these very high yield phrases, which, within these step one questions, correlate with certain answers. What does this have to do with language models? So I'm hoping that I'll maybe give some intuition about what a language model might also do in this type of situation. But to kind of go back a few steps, let's answer what is generative AI more generally. So we've seen a lot of discriminative AI algorithms within medical AI for a long time. As Shek mentioned, these types of narrow specialized models that can do tasks like image classification, for example, like a chest X-ray model that's able to classify pneumonia versus no pneumonia. But these days, we're talking a lot about generative AI, such as text-to-image models, which are able to generate high-quality images from text inputs, or generative text models that are able to complete sentences like once upon a time. And we're seeing a lot of these examples now make their way into medicine as well. So diffusion models, these very capable text-to-image models, are able to take text like small right-sided pleural effusion and generate very high-quality medical images that seem very realistic. And then we also have transformer-based LLMs, which is what I'll be focusing on for the rest of my talk. You're able to answer questions that a patient might have, like what is vitamin D3 used for? And so because these models have showcased such incredible capabilities, we're seeing a lot of people talk about what could be the potential role of these LLMs within medicine. Could they be answering patient questions? What role might they have to guide and help our research? A big question is, will they be useful within the clinical workflow more generally, as well as whether they'll be helpful within medical education? So we really want to be able to evaluate all of these use cases. And to do so, I think we need to think about a few different paradigm shifts now within generative AI, the first being how we train these models. And Chuck briefly touched on this as well. So you'll usually take like this untrained model, you'll feed it a ton of text data, unstructured usually, scrape from the internet to obtain this pre-trained base model, which takes a long time and is quite expensive to do. Once you have this pre-trained base model, you can do something called supervised fine-tuning, where you take question answer pairs, for example, and are able to align this model to answer questions that you might commonly see, for example, in a USMLE practice exam. And then if you want a chat optimized model, you will probably use some type of reinforcement learning techniques, such as RLHF, which uses human feedback. And so kind of in other words, you have like this textbook step where the model is like reading a ton of textbooks. Then you have a step where it's potentially like looking at a bunch of flashcards like a second year medical student might do. And then it's getting feedback from its attendings, for example, as it might on rounds. And from this pipeline, we've seen a number of new LLMs kind of emerge within the biomedical space specifically. Seen a number of models that are pre-trained on biomedical text, a number of models that are fine-tuned from generalist models, fine-tuned on biomedical text, and then also some generalist models that have been performing very well that have just done general pre-training, general fine-tuning, and then RLHF. And if you want to learn more or see some more models that could be relevant here, I've created a curated list on Hugging Face that you can check out. And one other aspect of these models is not just the model itself, which contains the weights and the architecture code, but also how we think about the systems that surround these models. So you might be familiar with an API like GPT-4's API, for example, that includes probably some type of moderation and guardrails or compute, as well as a chat interface like ChatGPT, where you're accessing these models through some set hyperparameters and system prompts. And why this is kind of important is when we're thinking about evaluating these models. Before, when we used to talk about black box models, we usually were referring to the actual mechanistic interpretability of the weights themselves. So how we have inputs and then outputs, but since there are so many weights, it's very difficult for us to really be able to understand how those weights are working together and how that architecture is kind of working. But now we're actually looking at these black box systems where we really don't understand what type of moderation is happening, what are the system prompts, what are the hyperparameters, whether the model is being updated itself. And so this is something that we need to consider when we're thinking about evaluating these systems versus models. The next paradigm shift that I would like to talk about is the data for generative AI models. This is one data set called the pile, which has been studied extensively. And while it has a ton of different types of text, you'll see that it also has a lot of biomedical text specifically. And so we think that a lot of these models are being trained on, even these general models are being trained on a significant amount of biomedical text, whether that's from PubMed, whether that's textbooks, whether that's scraped internet content from forums like Reddit. We also can take a look at the data for fine-tuning LLMs as well. So this is MedQA, one of the most popular data sets for fine-tuning and also evaluating models. And so this is using Hugging Face platform. You can search for different terms like apple green birefringence and take a look at what's really inside of these data sets as well. So this is like a classic step one question. And so now we can kind of have some intuition about, if you are a large language model, what you might see. And potentially it's no surprise that since a lot of these models are using a lot of medical data to be trained, that it actually does kind of sound a little bit like our second year medical student because it's reading so many of these textbooks and having so much of this, this data that's using these high yield phrases. And so if we're thinking about maybe ways that we can evaluate these generative AI models, like I said, we usually have been using USMLE, but is that the right method for us to really see if these could be used within medical contexts? There's some considerations we can think about. One is, what are we evaluating? So as I mentioned, you can think about evaluating the model, the systems around the model, as well as human interaction, such as prompt engineering or automation bias. You think about who is actually doing the evaluation. So many people use programmatic methods, which are very quick and are easy to do, generally using benchmarks. Think about using other LLMs to rate the LLM's output, which is an interesting method, as well as using humans, whether that's experts like clinicians or patients, for example. We can think about how we are evaluating the model, whether that's metrics like accuracy or F1 score, which can be easy to interpret, but have certain uncertainties around them as well. Rubrics are another way where people are rating models on things like quality or empathy. Feedback from humans, like thumbs up or thumbs down, or something more granular like edits. And then also you can compare model outputs from two models to get an understanding of how the models are doing. And finally, one major aspect of evaluation is also to think about why you are evaluating the model. Is it for task performance, human alignment, which kind of means like how is it answering the questions? Is it answering them well and aligned to what a human would want to have outputted from a model, as well as whether these models are outputting some types of adversarial data based on those inputs. And there are a number of issues with evaluating generative AI models, as you can probably imagine. So this is one aspect of evaluating some of these multiple choice questions, which you'd think would be pretty easy, but since generative AI, there's so many different outputs that can happen. There are a lot of different interesting choices that you can make when evaluating models. So I'd highly recommend, if you are evaluating models, to take a look at some of these resources. And finally, when we're thinking about evaluating models, I think it's really important for us to try to step away from using human intelligence as kind of a proxy for how we think about generative artificial intelligence, as we really don't have yet a good intuition about working with LLMs. So some of the things that people are still researching are whether LLMs are really able to do reasoning or whether it's a form of memorization. Whether the generation of confident but incorrect information is a big issue within medicine. This usually is referred to as hallucination, as well as there's a lot of different non-intuitive errors that between humans and LLMs that are still being discovered. So I think it's pretty unhelpful and potentially dangerous for us to think of anthropomorphizing LLMs when we're thinking about applying them into medicine. And so just to go back to these four phrases again, and what does it really have to do with clinical medicine, that is? Truly, these are really only one piece of the puzzle when you're thinking about a clinical picture, like a longitudinal clinical picture, right? Clinical care is much more complex and nuanced than these short patient narratives that you might see in a USMLE step one question. Some aspects of this, understanding and constructing the patient narrative itself is a very complex task. The data in the EHR is often incomplete, outdated, or incorrect. The ground truth diagnosis is also often not very possible, but still very important for a lot of these algorithms for us to evaluate them. There are a lot of differences in the practice of medicine by period of time or by location, whether that's in New York City, whether that's in California. There are a lot of different aspects, or whether it's like around the world. And then finally, medicine is still often more of an art than a science. So we really need some more rigorous, transparent, and independent validation efforts for the potential roles of LLMs in medicine. And so how should we go about thinking about this? So the question that I would like to pose is, how can we balance the strengths and weaknesses of humans with the strengths and weaknesses of large language models? And so when we try to answer this question, we should try to consider some principles of responsible AI. One being trust. So when we're thinking about reproducibility, it's important to try to use open source models or APIs as much as possible and not chatbot products due to the transparency issues. Include model information such as model access date as well as hyperparameters, as well as consider releasing your code and data set if possible. Try to match the tasks to the claims that you're making, as well as look and inspect your data. Also consider the potential for data contamination. Since these pre-training data sets are so massive, it can be very difficult to do this. And then also, we need, again, as mentioned, more independent verification and monitoring efforts for LLMs that are considered to be deployed into clinical contexts. And so one example of these types of independent efforts, Hugging Face has a number of open large language model leaderboards that we maintain. And we're going to be making some more within the clinical and biomedical context. So keep an eye out for that soon. In terms of safety, bias is a massive issue for large language models. This could be, differences in performance across different languages, across different patient demographics, such as race and gender, as well as the location and practice setting. Adversarial attacks are still a massive issue for large language models, such as jailbreaks and prompt injection. And finally, we still need to be very mindful of human and AI interactions, such as automation bias. Transparency is probably one of the issues that I'm the most passionate about. So I think we really need to start promoting more and practicing more good open science practices, such as good model and data set documentation, utilizing sharing platforms like GitHub and Hugging Face and PhysioNet for code, weights, and data sets, and also to share benchmarks and evaluation code if possible. And then also recognize the limitations of black box systems. They're still important to study, but we still do need to recognize the limitations, especially within reproducibility of studying them. Privacy is obviously a massive issue for these models as well. If you're using these for any type of clinical, workflows, please don't input any patient data into third-party APIs or chatbots unless you have some guarantees like HIPAA compliance or privacy, and also warn your patients of this risk as well. We're still having a lot of research being done around the regeneration of private data. And it's still unknown whether removing the standard PHI markers really constitutes de-identification, or whether there might be other aspects of de-identification we need to be thinking about. And this could be a potential role of synthetic data here as well. So I'm really looking forward to a lot more research being done on the role of synthetic data and potentially training some models of synthetic data. And finally, accessibility and inclusivity is a really important aspect of all of these efforts as well. So if you're a medical professional, I highly recommend joining some open validation efforts to take a look at the evaluation of these models. For example, Metatron was recently released. It's a medical model that has an open validation effort going. So would recommend checking that model out. There's a number of advocacy efforts for getting involved in health AI. If you're doing research projects, think about inviting diverse stakeholders early on, such as patients, clinicians, ethicists, researchers, engineers, policyholders. Consider creating a no-code demo so that folks who don't have a technical background can access and evaluate your model. And then also, if you're interested, consider participating in a lot of the different AI and medical education efforts so that clinicians can have more and more practical understanding of how to work with large language models and other types of AI models. And so finally, to wrap up, as we think about bridging this chasm between AI and clinical implementation, and obviously me being from Hugging Face, I think that open source plays an important role in addressing a lot of these responsible AI principles. And so just to close, I'd like to rehash Eric Topal's message in this paper, which is that progress is likely to come with the development of open source AI, trained on open data depositories and publicly shared algorithms. So thank you for your attention, and I'll turn it over to you, Cyril.